In my last video, I talked about how the double slit experiment was mind-blowing. How the particle passed through the slit depended crucially on whether someone was detecting the particle or not. In this video, I'm going to show you how scientists can not only undo that effect, but how it's related to time. So we're about to tackle a very tricky concept in physics, which involves the nature of space and time and whether the future can affect the past. But this is so tricky, I think it would be best if you viewed my earlier double slit experiment video. We saw in the previous video that a single photon traveling through both slits leaves an interference pattern, which means the photon is a wave. If we looked at which slit the photon goes through, we see a pattern that is consistent with the photon being a particle. We call the second experiment a which way study. This result is pretty freaky. Back in the 1930s, physicists like Niels Bohr speculated that human consciousness changed the result. We no longer believe that. Any detection of the slit the photon goes through gives the same result, including detection by electronic circuits. But let's make some changes to the single photon hitting two slits experiment. They're going to blow your mind, I promise. Let's add a crystal to the experiment, which turns the incoming photon into two photons, each with half the energy of the first one. These two photons are what we call entangled, which means that if you measure one, you know everything about the other one. The fact that one is yellow and one is red isn't real. They're actually the same color, but I use the two colors to clarify what I'm talking about. We then add two detectors called A and B, which measure not the photon hitting the screen, but rather which slit the photon goes through by measuring the cousin photon, which never hits the screen. If A and B are turned off, you see a wave pattern. That kind of makes sense, but if A and B are on and you look to see which slit the photon went through, you get a particle pattern. Okay, here's the first mind blower. Suppose you make the cables going to A and B very long, so the photon hits the screen before you can measure its cousin in A and B. If you do this, the result is unchanged. So what does that mean? It means that if you turn A and B on, detecting the cousin photon affects what the photon hitting the screen does in the past. This experiment seems to completely screw up causality. The particle or wave pattern is created by whether a detector in the future sees which slit the photon goes through. But there's yet another step in weirdness. What if you can erase your knowledge of which slit the photon goes through? What happens then, and how do you do it? You do it by adding 3 half-silvered mirrors. A half-silvered mirror will reflect half of the photons and half will pass through. You put 2 of them, one in front of the detector A and one in front of detector B. This means that the beams of cousin photons can go into the detectors or get passed along to additional instrumentation. You also add 2 new detectors, C and D. These are farther away from the screen than the A and B guys. You place mirrors in front of the beams of cousin photons, leading into a single half-silvered mirror. That means that the photons from A can either be reflected into detector C or pass through the mirror to detector D. Conversely, the cousin photons from B can either be reflected into D or pass through the mirror to detector C. You can see it in the red and yellow paths. C and D can see yellow or red. The bottom line is whether you see a cousin photon from detector C or D, you don't know which slit the photon went through. The addition of C and D completely erases the knowledge that A and B give you. So what happens if you turn off detectors A and B and look at only C and D? Since the detectors don't tell you which slit the photon went through, it once again acts like a wave. But C and D are a little offset, so you see the interference pattern only when you look at C and D separately. Furthermore, if the cables to C and D are long enough, the photons hitting the screen long before the cousin particles hit C and or D. So what I'm saying is the following. If you use A and B in the original experiment, you get a particle pattern. However, if you use C and D in this new version, you get a wave pattern. And detection in A, B, C, and D all happen after the interference or particle pattern is created. This bizarreness implies that in the quantum world, both location and time don't act like they do in our familiar world. Quantum mechanics can be considered non-local because of the cousin photons and non-temporal because the detection somehow changes the past. Now, the most important thing to state is that these are experimental results. You can discuss what they mean, but you can't deny that this is how the quantum world works, because without any chance of being wrong, this is how the quantum world works. So how can we explain the delayed choice and quantum eraser experiment? The simple and sadly unsatisfying answer is we don't know. Okay, so what's the answer? Like I said, we don't know. Could it be that the universe at the quantum level doesn't understand time in the way that we do? Is the universe super deterministic, which means that everything we do, past and future, is predetermined? Or getting even sillier, maybe the delayed quantum eraser experiment is just a bug fix in our simulated universe, which is kind of like the Matrix. Or it could be none of the above. Indeed, it almost certainly is none of the above. The real answer is almost certainly going to make all of our heads explode. Okay, so that was cool. I'm sorry that there's no answer, but there isn't, even for people like me. Some viewers claim that photons do not actually experience time, and that's a complex topic with some interesting features. It's a well-known feature that in Einstein's theory of relativity, different observers will experience time differently. Specifically, it's often claimed that an observer moving quickly will experience time more slowly than one that is stationary. This phenomenon is called time dilation. Now, there are a lot of subtleties and misconceptions in such claims. To help dispel those claims, I made a video on how time dilation is often misrepresented. And I also made not one, but 2 videos about the twin paradox, which deal with a seeming paradox of relativity, which seems to make contradictory claims. It turns out that this isn't really a paradox, but I'm not going to get into those here. I mention these videos because there's a ton of confusion about these topics. If you're interested, I strongly recommend watching them. However, what I want to talk about here is whether a photon experiences time. If it's true that a moving clock ticks more slowly than a stationary one, and a photon moves at the speed of light, is it possible that the photon is moving so fast that no time is experienced? To get a handle on that, we first need to understand 2 important concepts. The first is that in special relativity, there's a mathematical term that pops up all of the time. This term is called gamma. In this video, I don't want to get into exactly what gamma is and how it arises. I made an entire video on that. Basically, gamma is what makes all of the weird bits of relativity happen. It is written as gamma equals 1 over the square root of 1 minus the velocity of the object squared divided by the speed of light, also squared. That's what it is. Like I said, it's not super important to understand where the gamma comes from. Just know that if there's a relativistic equation, that gamma is going to be in there somewhere. So, let's see how gamma comes into play when we consider what goes on with a photon. If you're standing somewhere, perhaps waiting for the bus, and you see a photon go flying by at the speed of light, what happens with gamma? Well, we can put in for velocity, the velocity of the photon, which is the speed of light, which we always write as c. We can see that we get c over c, which is equal to 1. And with that, we see that the gamma reduces to 1 over 0, which is undefined. So that's the key point number 1. The equations of relativity don't work for objects traveling at the speed of light. That means that relativity theory also fails for photons. On the other hand, we can borrow an idea from calculus, which is called limits. While we can't use the relativity equations for objects moving at exactly the speed of light, we can evaluate them for objects moving at 98% the speed of light, 99% of the speed of light, 99.99 the speed of light, and so on. In principle, we could do the calculation at speeds that are 99.many times the speed of light. By doing this approach, you can see what happens as you get closer and closer to the speed of light, and use that to figure out what happens when you finally hit the speed of light, if you could, which of course you can. So let's do that and ask how long a super fast object will think it takes to get from Earth to the nearest star. The nearest star is about 4 light years away, so a person on Earth will say it takes 4 years to get there. How much time will a person traveling at 90% the speed of light take? Roughly a year and 9 months. How about at 99% the speed of light? A little over half a year. 99.9% the speed of light? About 2 months. We can continue this trend at the staggeringly fast speed of 99.9 more nines the speed of light. It will take a bit shy of 10 minutes. From this, we can conclude that in the limit of going at the speed of light, that a photon will experience 0 time. So that's pretty wild. Taken to an extreme, this means that a photon can cross the entire universe in 0 time. And it gets weirder. Not only does relativity predict that times will shrink, but it also predicts distances will too. Indeed, I made an entire video on this subject, which is called length contraction. A fast-moving object will shrink distances in the direction of motion, although not side to side. If we made a cylinder that stretched from here to the next star, we'd see it as 4 light years long, while the photon would see it as a circle with no thickness. Again, taken to the extreme, a photon views the distance traveled as it crosses the universe as having no thickness at all. In a sense, as far as the photon is concerned, it's everywhere along its path at once. Now we have to be careful since the equations of relativity don't apply for traveling at the speed of light, but hopefully you see that this limit trick allows us to get arbitrarily close. So I think we can say that a photon experiences no time as it passes from place to place as it travels through the cosmos. Furthermore, it experiences all locations along its path at the same time. Photons are ageless.